an AI-assisted telehealth solution for diabetic eye screening here in this country. Now, I need to declare a couple of affiliations. I'm affiliated to Auckland University. I work for the Health Board, Auckland District Health Board, which is where a lot of this work was done. I'm on the committee which developed the diabetic retinopathy eye screening guidelines for the Ministry of Health here in New Zealand. And I'm also a co-founder of Toku Eyes, who developed the AI that we're going to speak about. Now, there is a Maori proverb, which in English said, "What is the most important thing in the world? The people, the people, the people." And that ethos is really at the centre of what we've been developing here in New Zealand. And I love this quote from Professor Noel Sharkey from Sheffield, who says that decisions about people should be made by people. AI should be considered a tool to assist human decision-making, not its replacement. So that really is central to the whole project that we've developed here in New Zealand and the role of AI within it. Now, before I take you on our journey, I thought it's important just to introduce you to who we are. Now, it's important to say that New Zealand is not Australia. Although we do share very similar flags and we are sitting here at the bottom of the globe, New Zealand sits there bathed in the middle of the South Pacific. Anybody who knows anything about New Zealand may know a couple of things. You may be very familiar with the Lord of the Rings. We obviously play rugby. We have an indigenous people called the Maori people. And we have a Prime Minister, Jacinda Ardern, who is very prominent at the present time. We also share or are blessed with great natural beauty, with lakes and mountains and wonderful seascapes. But that's not New Zealand. So who are New Zealanders? Well, we're a country of about just under 5 million people, and the vast majority of our population is concentrated in 1 or 2 urban areas. These urban areas obviously have high infrastructure, quite a developed healthcare system. But as shown by this map here on the right, we are a very rural people too. And actually where the social deprivation is in these rural areas. And these rural areas are, as you can see from our geography, often quite difficult to reach. So we've had this dichotomy in this country. We have urban centres which are well served with good infrastructure and medical services, and we've got a rural poor, which are difficult and hard to reach and not well served by existing infrastructure and medical services. We are a very diverse group of people. This is an old slide, but it does give you an idea of where we all come from. So as you can see, we come from around the world with populations from Europe, North America, and Asia. As a result, we have great cultural diversity, and this diversity is growing. The predominant population is European, but we have significant ethnic mix from across the board. This is a slide taken from the people groups in Auckland, and as you can see, we're really a microcosm of the world. So sitting down here in our little island, or a set of islands, we are a very diverse group of people. Coming to the core of what we're talking to today, it's no surprise to everybody here that we're in the middle of a global diabetes epidemic. That won't come as news to you. And the problem with diabetes is growing rapidly year on year, with really quite amazing projected outcomes of how many people are going to be living with diabetes over the next decade or so. As you all know, a significant number of patients with diabetes will develop sight-threatening conditions, and it's therefore no surprise that diabetes is the leading cause of blindness in patients of working age. Now that statement, though, is no longer true in the UK. And in the UK, it's actually inherited retinal diseases, which are the leading cause of blindness in adults of working age, not diabetes. And much of this is attributed to screening. The UK has had a systematic screening program for the last 15 years or so, and as a result, they're picking up the changes of diabetic retinopathy early and treating before moderate or severe visual loss occurs. So screening works, but the process of screening is a rather laborious process. Essentially, you have to know who all your patients with diabetes are. You have to then bring them to a facility where you can take a photograph of the back of the eye. That photograph has to be stored, has to be then passed to someone who is able to read it, and that report then has to be passed back to the screening program. Now, in New Zealand, we take 4 images per screening episode, a disc, a macular-centered image on both eyes. And before we started this project, it was taking somewhere around 6 weeks for that report to find its way back to the patient. Also within screening, anybody who does anything with diabetic eye screening will know that the vast majority of patients who we screen have none or minimal disease. So we spend a lot of time looking at normal images. Indeed, only a very small percentage of images actually have significant disease which needs eye clinic review. And there's a small group in the middle who it can be sometimes difficult to tell apart. These are particularly patients with macular disease, because of course when we're looking at maculopathy, we're looking at surrogate markers of tissue edema. So in New Zealand, in addition to photography, we also have OCT as part of our screening process, and this certainly makes it then much easier for the graders to triage whether the patient has sight-threatening macular edema or whether it's just drusen or macular reflex. Now, New Zealand, although we're a small country of only, as I say, just under 5 million people, our healthcare system is divided into 20 different health boards. Those different health boards have a very different urban-rural mix, and within each one of these health boards, we've got individual screening programs. At one level, that may look as a strength because we've got lots of different programs, but as you can imagine, many of these programs are serving relatively small numbers of people, and they can be reliant on 1 or 2 key individuals. So they can be slightly vulnerable to people leaving or camera systems falling down just because of the scattered nature of the programs we have. There can also be very little consistency sometimes between the reporting standards. So New Zealand has had a program, a diabetic eye screening program for the past 12 years or so. And as I say, we have them established in all our DHBs, but national data suggests that up to 40% of our patients with diabetes in New Zealand are currently not being screened. And of course, this means that patients with diabetes are losing vision unnecessarily, which has both a human and societal cost. And when you look at the problem, you can really see there are 2 main factors here driving this. The first is the human factors. It's difficult to train or get trained personnel to read the photographs, or at least read them economically. The second factor we have is we've got geographic factors. We've got lots of isolated rural communities which are hard to reach and poorly served by existing infrastructure. So our fixed camera systems were not really serving our rural poor terribly well. We also have more roadblocks. This whole process is very bureaucratic, and you need multiple spreadsheets passing images onto graders, graders onto reports, reports back to the central referral hub. So this whole process was slow, laborious, and quite difficult to manage. So for a number of years, we had a vision and said, okay, can we revisit this screening pathway? Can we collapse it? Can we get to a point where we can simply take the images and those images be read on the fly so that we can report back to our patients and get the process moving more rapidly? Can we make it mobile? And essentially, we were looking for these key features. Can we improve our productivity? Namely, can we get a system which would deal with all these normal images quickly? This would leave us with a smaller number of patients with significant disease that we can concentrate our resource on. Can we develop a system which was scalable, which means that we could take it around the country, we could go from 1 center to 10 centers very quickly. A process needs to be fully automated, it needs to be flexible, facilitate OCT, and it has to be acceptable to our patients, to ophthalmology services, and to our funders. And for example, with ophthalmology services, our key problem we have here is that our ophthalmology services, being a public sector service, are overwhelmed already dealing with things like macular degeneration. And the last thing we need is to push a lot of patients from screening into the eye clinic. So we needed to be able to gatekeep appropriately, and we needed to have a solution which wasn't going to overwhelm our tertiary care ophthalmology services. So of course it will be no surprise to people in the audience to hear that AI is going to have, or starting to have, quite a major impact on ophthalmology. And in many ways, it's surprising it hasn't had more impact just yet because of the power of AI. Now, about 2015, we really started to think seriously about how we could change our model of care. So we had a clear idea of where we wanted to go. The trouble is, we spent a long time not actually having any idea of how we get there. And I'm sure any of you who have been dealing with large projects can have a moment like this when you're wondering how you're going to get from A to B. Fortunately, in Nature Medicine, there's been published a much nicer map than the one we had right at the beginning, which gives an idea of how you get from a concept to actually having a good healthcare sort of machine learning AI sitting within your system. So I'm just going to use this roadmap to sort of illustrate that journey. So we started in 2015 with a problem, and that problem was, could we use an AI-based system to help reform our diabetic eye screening programs? So of course, the next step is to develop a useful solution. Well, we thought there's no point developing a new solution. Can we just use an existing diabetic eye screening AI? Now, at that stage, I knew very little about what AI could do. I knew a lot of the hype, and so I had to spend a little time understanding what AI is. And I think it's just important just to spend a few minutes with you. I appreciate there'll be members of the audience who understand this very well, and there'll be people who perhaps less so. So I'm just going to spend a few minutes just talking about AI. Now, AI is not new. We've lived with it for a long time. And essentially within AI, there are different types of learning. The learning that we are perhaps more familiar with is something called machine learning. Now, with machine learning, what you do is carefully define the features of what it is you want the machine or the computer to identify. So for example, let's take maybe a black t-shirt and a pair of trousers. We can identify the features of the image which makes this a black t-shirt. We can also identify the features of this image which make this a pair of trousers. So then if you give the computer different types of images, it will pick out the black t-shirt and the trousers. The trouble is, if you make the t-shirt blue or you make the trousers slightly shorter and change some of those features, the machine will no longer be able to recognize what you're looking at. So it will pick out very defined things, but that's not terribly flexible when it comes to processes such as medicine, where there are gray areas. So the part of AI which has really transformed, particularly medical services or medical applications, is deep learning. And in deep learning, the machine itself learns what the features are within the image that define it as either, for example, a t-shirt or a pair of trousers. What you need, though, is lots and lots and lots of images labeled t-shirts and trousers, and the machine will try and work out eventually what makes this part of an image a t-shirt and what makes it trousers. So then the question is, well, how does a computer learn? Well, the computer scientists who first built these large convolutional neural networks, they use the brain as their inspiration. So of course, within the brain, the core component of the brain are the neurons. The neurons have dendrites, which are collecting information, which they give to the cell body. The cell body integrates those inputs, and there's an outcome as a result. So within a computer network, we have a very similar thing. So we have a node, which is really a mathematical function. That mathematical function has numerous inputs, and depending upon the weighting of those inputs, it produces a certain output. Just like in a brain, these neurons are all connected up together. Within a computer network, these nodes are all connected together as well within different layers, finally giving an output. So the input layer would be the images, for example. The hidden layers would be these various mathematical equations, and the output layer would be, well, is this a t-shirt or is this a pair of trousers? So what I thought I would do is just talk you through how this network learns. For example, let's take this example here of a chicken. So the way the neural network will now start to develop this is it breaks that image down into multiple pixels. And for the sake of this illustration, I've just overlaid a grid. But what it will do is take components of this picture, break it down even further, and start to look at individual pixels one at a time with different filters to try and ascertain what is it about this image which makes this a chicken. So having done that, what it does, it will take this image, you feed the various components of this image, those various pixels into the computer system, and to start with, it will guess. It knows that it's going to be a chicken, but it doesn't know really whether it may be something else like a dog. So to start with, you feed all these bits of information in. The computer guesses it's perhaps not much better than chance, but it learns that, okay, the output should have been a chicken and not a dog. So it goes back through the system and says, okay, what were the relative weightings within those different pixels, which made it more likely to be a chicken as opposed to a dog? And basically it does this multiple times until eventually the input balance, or the balance of those various inputs, is such that the outcome is very likely to be a chicken. So there we are. That's summarized a lot of computer science in just a couple of minutes. So having understood briefly what the AI is doing, then we have a question, well, how do we measure the efficacy of a healthcare AI? And the answer is, it's only as good as the data it's trained on. So for those of us clinicians who are not so familiar with judging AI, I would encourage you just to continue to look at it like you would any other medical data. You want to know, okay, what's the original data set? Is that data set sufficiently big such that I can generalize to my patients? For example, in the case of a chicken, if all I did was feed my AI a picture of a red chicken, it will be really good at picking red chickens, but it might not recognize a black chicken. Secondly, is this AI trained on the patients you intend to use it from or tend to use it on? And again, that's very similar to a drug trial. If you're looking at a particular drug, is it going to be applicable to the group of patients that I'm going to use it in? And I would argue, if it's not, should you trust it? An example here, for example, maybe a facial recognition AI. The facial recognition AI, which is trained in Europe, trained on European faces, may be good at recognizing a European face, but it may not do terribly well recognizing an Asian face. Similar and related to that, does the data set have an inherent bias? And it's important to actually be aware of this, because the AI is making associations. So it can make any association, and it may not be making the association that you assume it would do. The example here I'd use is an American military. As you wouldn't be surprised to learn, the American military were early adopters of AI. And one of the earliest AIs they did was to say, well, can we recognize a tank in an image? So they had a whole series of images, and at the end of it, they thought they had a pretty good AI which would tell tanks from not being tanks. What they didn't realize is that all the images that contained tanks were darker than the images which didn't contain tanks. The AI, in effect, was not picking out tanks at all. It was just picking out the sort of duller, darker images. So you have to understand the background of the patients that it's being trained on. I think it's also important to ask the question, does it add value to what it is that we're currently doing? I appreciate AI is very glitzy, but at the same point, if it doesn't actually add value to what we are doing in this current system, perhaps it's not the answer to the problem. And as a result of the above, there are ethical considerations. For example, where is the data being stored? Are you using a provider who's going to copy your data? There are issues about data privacy and data sovereignty. So having thought about that, we realized that actually the existing diabetic AIs were not going to be applicable to our patients. Certainly none of the existing AIs are trained on patients from Polynesian or Maori extraction. As a result, the data set will have an inherent bias. The existing AIs would not dovetail very neatly into our existing diabetic eye screening program, and because they had a lower sensitivity, they were going to generate a number of false positives and negatives, and that was going to present a problem to us. And finally, we had ethical considerations. Certainly in New Zealand, our system has to be stored locally because of data sovereignty issues. So we come back to our roadmap and quickly ruled out the fact that we couldn't just plug in an existing diabetic eye screening AI into what we were doing. There were also cost considerations. So we then started to think, well, maybe what we need here is a bespoke AI for New Zealand. And as we began to think about this, we realized that we had a very suitable data set because, of course, we've been running diabetic eye screening for over a decade. We had great collaborators within clinics and within academia. And of course, we're working closely with the diabetic eye screening programs, and we therefore had great user engagement. And we thought this will give us an opportunity for developing an AI which would really would dovetail very nicely into the programs we're currently running. So we set up this project, THEIA, and the aim of our project really was to develop an accurate diabetic grading AI, which would be operator agnostic. Namely, it didn't matter who took the photographs, that image acquisition process would be fully automated and would identify when an image of sufficient quality was taken, and therefore allow that process to be seamless. We didn't want to be beholden to one camera system. Throughout New Zealand, we have multiple camera systems in use. And the last thing we wanted to do was have to go and buy a whole new set of camera systems. We also wanted to have the flexibility of changing cameras in time depending on our needs. So we decided the system had to be camera agnostic, also grader agnostic. It was not beholden upon one grader to generate all these images. As you can imagine, there are multiple stakeholders in a project like this, so we had to spend quite some time negotiating ethics, and we finally got approval from both national and local bodies to proceed. So we started out with a training set of about 170,000 images from 40,000 individuals. Every one of these images was carefully labeled with their diabetic retinopathy, maculopathy grade. And we use a grading system from 0 to 5 for both retinopathy and maculopathy. So we have a very granular grading system in New Zealand. We also had a validation set of about 60,000 images from another 21,000 individuals. The original data, as I say, with AI, it's always really important just to look at the demographics of the data set you're using. Is it applicable to your data set that you're going to ultimately use the AI in? And not surprisingly, our data set was very representative of patients in New Zealand who have diabetes. It's also heavily weighted to patients with type 2 diabetes because, of course, that's the predominant type. And as with any sort of medical screening service, the vast majority of people are normal, which creates some issues for the AI and some technical issues there that the AI boffins amongst you will be very familiar with. So we ended up with a set of images that was very representative of people with diabetes, so we were now confident that we could proceed. As I said, our retinopathy and maculopathy grading system in New Zealand is very granular, R0 to R5 on the left, and in the right-hand side, maculopathy grading M0 to M5. So we developed our AI, which would grade to the Ministry of Health grading classification. We had to do that for New Zealand, but equally, we felt that was rather complex, particularly for a primary grading system. So we also put alongside it, we collapsed those grades and put alongside it a traffic light system where red was this is a referable image, amber, this is an image which may need referring, and green, this is an image that does not need referring. I'll just talk you through the design of our AI. It's important to realize that AI is not a single AI. There are really ensembles of AIs to produce these processes. So the first AI we had was an image check AI. So we really had to make sure that the image was of sufficient quality to be read. And that's a really important point, because if you're having to use a human being to grade the quality of the image that you feed into the AI, then you have lost a lot of the utility of the AI, because you need someone to recognize what is a good image. So we had an AI which would recognize what a good image is, that allows the system to proceed seamlessly and automatically. We also had to deal with the fact that we had multiple different cameras. Of course, every camera has different flash, has different color balance, so we had to normalize that image. And then having done all that, we then passed the image to our classifiers, and we had a jury of classifiers, and we were weighing up the jury results before we allocated the image as being healthy, non-referable, or referable disease. So this is an example of patients' images that were deemed to be non-gradable. Of course, every time you take images, patient can blink, so you get a lot of images of eyelids. Patients can have significant disease. And certainly in New Zealand, when we got patients who we're struggling to get images of, we'll often take an anterior segment photograph as to explain why. And of course, in this case, we've got significant cataract. If patients do have significant cataract or lens or media opacity in New Zealand, we do have slit lamps services running alongside. So there'll be a small proportion of patients who, for whatever reason, are not suitably or suitable for screening with photography. But let's assume we've taken a good image. That image, for example, here, this image is then normalized with Gaussian filters, and then we pass that image to the AI. Now, what I've got here by showing the AI map is something called an attention map. And this allows you to see what the AI is making its judgments upon. So as you can see here, the AI is concentrating on all those new vessels at the disc and a few other bits in the periphery. So we are confident that the AI is making the right associations. It's looking at these new vessels and it's using that to decide the grading of this particular image. Now, of course, so far I've been talking about images, but of course, within our system, we have two images per eye. So we've got a macular image and we've got a disc-centered image. So as part of our process of reporting, we have to aggregate the results from both, not just the macular disease and the retinal disease, but also whether it's the macular-centered photograph or the disc-centered photograph. Having got a grade per eye, we then have to aggregate that to a grade per patient, and it's that which is the ultimate outcome for our patients. This just puts that process in a slightly more complex form, and the reason for showing you this is to say that we started off with 22,000 images in this particular simple sample, and of those 22,000 images, only 2,000, either 1%, were excluded because they were not gradable or deemed gradable by the AI. So we were rejecting very, very few images. So having passed through that, what was the results of our application? Now you can describe the results of AI processes in many different ways. No one way will really give you a full flavor of what the AI is doing, but receiver operating curve is one way. As you can see, the receiver operating curve for detecting retinopathy is very, very neat. That for maculopathy, less so, because that's where a lot of our uncertainty when it comes to grading pops in. Certainly when you're looking at patients with young patients, you've got macular reflex, which can look very similar to exudate. We've obviously got a lot of patients with drusen, epiretinal membranes, etc. But to summarize that performance, we ended up with an accuracy of 98%, reasonable specificity, high sensitivity, and most importantly for us, a very high negative predictive value. The negative predictive value was very important because we needed to know that if the machine said the image was non-referable, then we could be very confident that this patient did not have disease which was going to be missed. I've showed you an attention map before, but we can basically generate attention maps for every single patient that we do. And that helps us to look at the AI and say, is the AI looking at what we believe it should be looking at? And here's just an example here. The two on the left are the retinopathy grading AI images, and the one on the right is the maculopathy grading. So we can use these images to explore this so-called black box phenomena. What's the AI doing? Is it making the right associations? Can it therefore be trusted? So here's an example of one of our patients who's gone through, and what the AI does, it reads the retinopathy grade here on the left, it reads the maculopathy grade here on the right, and produces a report. So this is the report that THEIA will generate. As you can see, it's producing down on the bottom right-hand corner a traffic light system as to the likelihood of this retinopathy being referable and the maculopathy being referable. And I think we'd all agree that this is an image with referable disease and flagged up red. We can see also here there's lots of information, there's lots of different ways of presenting the results. As I said, we're using a jury system of 5 different AIs to produce that result, and that result therefore produces a probability map of what the results is. And if you look at the probability of the jury, you can see the vast majority of the jury felt that this was R4, which is severe non-proliferative disease, with a reasonably significant probability that this could actually be harboring proliferative diabetic retinopathy. However, as exciting as that is, the real gain of our system are these patients, those who are deemed to be normal. So here we are, the probability of this map is the likelihood that this patient has no retinopathy. Furthermore, they have no maculopathy. Bearing in mind that 70 to 80% of patients going through a screening program have no referable disease, being able to pick up these patients quickly and with confidence really is where the main gain of AI comes into from our perspective. So because we've got a negative predictive value of 99.8%, we can have very high confidence that if a non-referable grade is issued, then that is correct, i.e. we're not going to miss referable disease in our cohort of patients. Of course, there's always grey areas. For example, here's a patient here with suspected macular disease. Is this exudate or is this drusen? So the AI has said there's no significant retinopathy going on here, but there is a possibility that it may have significant maculopathy. Within our system, what that does is prompt the photographer taking the images to take an OCT. Again, the OCT is completely automated, so it doesn't matter who's running that program. They don't have to have the knowledge to know when to take an OCT. The AI prompts them. That then generates OCT, which allows us to then grade appropriately. So, as we continue our journey, we end up now, not too far away now, in terms of we have an AI that we put through rigorous evaluation and we felt ready to deploy. So how to deploy AI within our screening program? So the process is illustrated in this slide. The patient comes along and has a photograph taken. That photograph is stored on the local computer. It's then transferred by a custom user interface into the cloud and the inference read. The inference is then produced back, and within 10 seconds, the person taking the photograph has the results. And of course, those results can then be handed straight back to the patient. In this case, they have no significant disease and on their way out can make their next screening appointment. However, in cases like this, we have significant disease, both for retinopathy and macular disease, and this report is passed to the human grading team. Ideally, that human grading team is also available on the fly, that the AI is linked on the cloud to a reporter around the country, and so around the country would have one retinal physician whose session is to be reporting on the AI images that come through from around the country, and they will then report back to the grader. And again, before the patient leaves their diabetic eye screening appointment, they've already got the results of their grading, and on the way out, they'll make an appointment to the eye clinic. We believe it's very important that you've got a senior, or at least an experienced retinal doctor making these decisions, because it's that person who's going to be the gatekeeper for the eye clinic, and certainly we don't want to be overwhelming our eye clinics. So we had an old system which was taking 6 weeks to find that 5 or 6% of patients who needed to be sent in, and now we have a system which finds that 6% in 10 seconds. So essentially, by integrating an AI system within our diabetic eye screening programs, we've allowed our diabetic eye screening programs to work faster and smarter. And it does that because the AI is providing rapid triage of normals. So it's increasing the productivity and cost effectiveness of the clinician reading the images. Instead of having 20 different clinicians up and down the country gatekeeping all these images, we now have one person, and that one person is doing it for the entire country and is doing it on the spot. So we have a point of care which is consistent around the country. We've also, the AI transforms this fundus camera into a smart diagnostic platform, and we can use any existing camera system. We're not having to go and buy lots of new cameras to facilitate this. Furthermore, we can integrate it into our existing systems in terms of OCT. And what it means is that we can send this camera system anywhere into any of our rural communities, and we don't have to send a trained nurse or photographer to do it because the AI is telling them when they've got an appropriate image to be read. So it really allows us to then push this right out into the communities, which makes it very scalable. So we're at a point where we're ready to start deploying our system, which is really very exciting. So the dream was, or the vision was, to create this unified, automated, scalable system that would allow our diabetic eye screening programs to work smarter and faster, to allow it to be disseminated around the country and to be delivering results very quickly, and at the same time protecting our eye clinics from being overwhelmed with multiple false positives. So as I land this presentation, I think there's just a couple of lessons that I feel are worth sharing about what we've learned on this journey, and there are of course many others, but I think these are the important ones. We had to learn what a good healthcare AI looked like, and we feel it's one that is trained and tested locally. You can therefore rely on it, and it's going to be representative of those who it's intended for. That's really important when it comes to whether this is going to be an acceptable AI solution for our patients. We believe a good healthcare AI is one which is not dependent upon a particular operating system or camera, because otherwise it makes it very inflexible, and then you're beholden to that manufacturer forever. I think it's one that has to fully automate the process. The more human involvement you have, the less scalable it is. I think it's really important that you actually understand what's going inside that black box of the AI, and that you can interrogate it and understand it for yourself. And it has to be one that respects the data sovereignty laws of the country. It's not a system that's going to be leaking data and sharing it all over the place. I think it's also important that this solution has to solve problems, not create new ones. At the end of the day, the AI there is a tool that's going to assist us. I like to think of AI as a clinical assistant tool rather than being a take over the world, one ring to rule them all tool. It's important to say as well that multidisciplinary collaboration is the key. It's a very exciting thing to be involved with people from lots of different disciplines, and I certainly have enjoyed the journey, but we couldn't have done this without any of the people represented here. And finally, it has to be acceptable to our patients. The last thing we wanted to do was to be on the front news headlines of our local papers with our machine having missed it. So it had to be something that was not going to miss disease, acceptable to our patients, to our funders, and to the clinicians. I think it's important to acknowledge the team. These are just some of the really key people. There's been lots of other people involved. Obviously, we have a clinical team. These are my colleague, Dr. Ole, who is a diabetologist who's been very helpful. My two fellows, Sophie and Moaz, and I have a very large technical team as well, consisting of AI engineers, commercialization experts to help us actually through this journey of developing and gaining the funding to develop this. And of course, my co-founder, Ihsan, as well, who without him, really this journey, we wouldn't have got very far down it. So thank you very much. I hope that was helpful, and happy to take any questions.
Thank you, Dr. David, for this very interesting journey. And I think that the map that you showed in the presentation of how you started and then the progress you achieved in a very short, considerably short duration, starting looking at the problem and then going into addressing each problem that you go through in your pathway. And I feel that looking at this, and when you started and how you reached this level is makes people interested and excited to have their own experience, because it seems like we've been shown in a lot of media sources and as we see in a lot of the meetings, that AI seems to be something so complex that you can't really work on it and build it and have your own. It's like it's something that's unique, and you need to leave it to whoever is the expert in that. And you showed that you started in the beginning knowing nothing about the subject, and then addressing, the AI per se, and then addressing the people and forming the collaborations, and then getting to a stage where you have a fully operational system which covers the whole country. I would also like to mention that there's a lot of similarities between the nation as New Zealand and ours, because you basically have a lot of rural areas, and the distance is considerably big between big cities, and getting access to the care is difficult to many of the population. And now knowing that we're in this unfortunate pandemic, this actually has made the role of telemedicine a very important part of how we should look to the future.
Mm.
I believe that the most important message to my fellow ophthalmologists is that we can say that that AI will not replace ophthalmologists, will
Correct.
not replace the optometrist, and basically it's, as you said, a tool that we can use. I would like to mention here that the floor is open for any questions, and I've got a couple that I've written, and I'm gonna address those. I would also like to address our friends who are in vision science, who may have some questions that are a bit technical. I will store these and forward it to you, probably to be answered offline.
That'd be great. Yeah, very happy to take those sorts of questions. At least my technical team will be.
That's very nice. So one question that I got from one of the colleagues, and I'm not sure what the term you meant when you said that you will have economic reading of the fundus images. What did you mean exactly by this term?
Yes, of course, the difficulty with screening is traditional screening is finding people to read those images. Particularly in the rural communities, you've got a very small number of people are able to do that. And of course, they're already very busy doing other things. So in New Zealand, for example, we have small rural, like a small rural town may have 2 or 3 ophthalmologists covering a very large rural community, and maybe having 2 or 3 ophthalmologists to cover 200,000-300,000 people. So they're already very busy doing their normal day job of seeing patients. And so trying to persuade them that actually what they really want to do is spend half a day reading lots of normal images is somewhat challenging. So we also in New Zealand have optometrists. These are people who are selling glasses, but they do a lot more than selling glasses. They are also providing tertiary or sort of primary eye healthcare. But they're business people and they make their money selling glasses. So again, trying to persuade these people to not sell glasses for a day and read our images was quite challenging. Simply because we couldn't pay them sufficient amount of money to read, say, 200 images to make it profitable for them. So that was the problem we have. We do have some around the country people who could do it, but not people who would do it for the price that we could pay.
So given this situation, do you still have readers who are not optometrists, meaning that those are people who were trained for reading through a reading program, maybe high school graduates who will be doing this kind of situation? Or now that you've established your AI, you will feel more inclined to have more specialized people working on your program?
Yeah, that's a really good question. So the traditional model is you'd have a series of technicians reading and grading these images. You work hard to identify people who are willing to do this. But the trouble is with, particularly in our smaller regions, is if that person goes on holiday or if that person for whatever leaves or retires, then you have a big hole, which is then very difficult to fill. So it does leave you with succession problems and it does leave you vulnerable. So that's the problem with that system. These people do need to take time to be trained and get to a point where you're confident that they are accurate. So of course, the beauty with the AI is that the AI replaces a lot of that personnel. And that's not to say we get rid of those personnel. From our screening program, we're not screening 40% of our patients. So even making our screening program more efficient, we're still going to have plenty of work for those people to do. But actually, we've now made their job more interesting because they're actually looking at many more of the diseased photographs, not all those normal ones. And that then allows them, because they're then engaged with the patient at the time of the screening, they're the first port of call. So they're the one also organizing their eye clinic appointment, their appointment with the diabetic nurse. So we changed their role. So we haven't got rid of them. They're still very important people, but they now have a much more interesting role, which actually makes it much easier to recruit into.
Oh, that's important for even retaining those individuals, because it can be very boring
Yes.
job to read those images. Questions from our retina colleagues. Dr. Mohammed Al-Ajmi was asking about the maculopathy. How did you label them, and did you use specific labeling for diabetic macular edema, or is it just maculopathy? And then where would you put did you employ or deploy the OCT in this as a screening tool in your primary screening?
Yeah, very good questions again. So as you know, all our retinal specialists will know that our grading of maculopathy really dates back to early house EDTRS. So now a lot of our maculopathy grading is designed to pick up patients who've got potentially laserable disease before it becomes diffuse diabetic macular edema. And of course, anti-VEGF has changed that whole paradigm of how we monitor diabetic macular edema. So all our images, of course, our images go back to about 2008. All our images were graded according to the New Zealand grading system for maculopathy. In basic terms, we've got M0, which is completely normal disease. M1 and 2, you've got microaneurysms within the central macula. And M3, you've got exudates which are not within one disc diameter of the fovea. M4 and 5, you've got exudates within and under the fovea. So what we're doing here with our maculopathy grading is, of course, we're looking for hemorrhage and we're looking for exudate, essentially. So that's quite useful because most of the other important macular diseases that we see, branch retinal vein occlusion, diabetic, for example, macular degeneration, certainly in New Zealand, that our AI will by default pick up those patients too, because they'll see exudate or hemorrhage within the central macula and flag that up. But essentially what we're looking at is surrogate markers of tissue edema. So of course, one of the issues we had is we're having a significant proportion of our patients coming out of screening with, is that an exudate or is that a drusen? So we put OCT alongside our screening program a number of years ago because it really reduced those patients coming out. Now, the big problem we have, and I'm sure you have too, is that our medical retina services are overwhelmed already. So we needed to make sure that we were only seeing those patients who really needed to be seen. So OCT is integrated into our eye screening program. Many of our cameras are OCT fundus camera systems, like the Triton, for example. So we can just flick the button and just take an OCT at the time.
So this is an investment you've made in the beginning, having both in the same setting, probably to address later subjects like these. So in your opinion, you think that having both machines available in the primary screening would help a lot in lowering the number of the patients that needs to be referred to another.
Correct. It's all about managing your patients locally. In New Zealand, some of our patients will have to travel 300, 400, 500 kilometers to get to see an eye specialist.
This is a very similar situation here.
Exactly. Yeah. So why have these patients travel 500 kilometers for the sake of an OCT? OCTs are expensive, but they're not that expensive, and we can take the OCT out rather than bring the patient in. Also means that we've not got valuable real estate in our ophthalmology clinics full of people who don't really need to be there.
Okay. Another question. This is from one of our data scientists who is interested in. She had a couple of technical questions. I will refer to those to you later. But she was asking about, in terms of the patients you examine, is there, when you were teaching the model, did you get a feedback of would this fundus image represent a certain ethnicity, or were you able to link that in a clear way? And this will take us to the other question, meaning that if you believe that, this means that the ideal situation would be having your AI for your own population. You can't go to this one solution that fits all.
Yeah. So, there are multiple nuances to this. So, one of the first projects that we published was, well, can we detect if our patients smoke? So we knew if our patients were smokers, and one of our first projects was, can we just tell on the basis of a fundus image whether a patient is a smoker or not? And the answer was, just like Google, yes, we could. Can we tell ethnicity? Yes, we can. There's lots of information that we can draw out of those images. Does that? The issue here about ethnicity is important because within New Zealand, it has to be said that there are certain ethnicities which come from lower socioeconomic classes than others. So if you have a healthcare AI which is designed on a European data set. And let's face it, most big data sets come from private clinics because that's where everybody gets investigated and gets all these pictures. So if your data set is drawn from a European population who can afford private healthcare, that's not representative of the patients who are in our rural populations who have diabetes. And so the problem you have then is maybe if you had, for example, Maori or Pacifica not included, how would they be represented in your data set or in your AI? Your AI may work very well for people like me, but it may not work very well for people who are of Maori and Pacific. So in many respects, your AI will drive existing health inequalities, which is the inverse of what you were trying to do in the first place. So it's really making sure that the AI is representative of the patients you've got so that you are going to solve inequalities, not make them worse.
I see. So yeah, I think this is a very important part when you tackle a subject like this. Another question from I had a lot of questions here about the public response to the process, in terms of did they think that this is a nice invention, or they were skeptical about the machines, and them not being very accurate. Same goes for the physicians as well, the ophthalmologists.
Indeed, I think actually our greater reservation was from those involved in screening at the present time. The public tend to be fairly accepting of these systems, that they just think it's really neat that they're now going to be able to get their results on the day rather than waiting 4-6 weeks. It was more our colleagues within the clinical services who were rather skeptical. So they needed winning over. They were concerned for two reasons. One, would they still have a job? They were naturally concerned that the AI was going to come along and just make them redundant. And secondly, they were rather skeptical that the AI would work because, it's just this black box and you plugged it into a machine, and is it actually going to be doing what it should do? So we've had to do a lot of work with our end users, so to speak, to make sure that they were happy with it. That in itself has been a really, really useful exercise because at the end of the day, they're the people using it. So they've given us lots of really useful feedback about what the user interface looks like, what the traffic light system should represent, how we should present that to the patients, how we should present results. So actually, it's really quite useful sometimes to have skeptics on board because they bring very valid questions and concerns. We're not going there and say, we've invented this, here it is, use it. We're actually engaging them and said, okay, this needs to address your concerns. Your concerns are valid because you've been doing this for a long time. Well, sometimes the concerns aren't valid. They're just anxious about their jobs. So it's reassuring them that this is a tool that's going to make their job more interesting. And from a patient's perspective, they're just very pleased that they're getting accurate results very quickly.
Cool. Question from Dr. Fatma Shamlan. She's addressing the thing that we all face, where if the media opacity does not allow it, how do you go about dealing with those patients? I mean, the process that you go through.
Yeah. Again, that shows, for all of us involved in diabetic eye screening, well, in retinal disease, isn't it? There's corneal opacity, there's lens opacity, tear film issues, all of those can degrade the quality of the image. So we have to also, pupil dilation is another big factor. Some of our patients will have small little pupils, a bit of lens opacity, and it's almost impossible to photograph them. So there are a number of patients who still cannot be photographed, or you can't read that image of sufficient quality. So we do have slit lamp clinics running alongside. So we'll have patients coming along, and there'll be a very small number of patients who we just can't photograph, or they've got a physical disability, which means you can't get them to the slit lamp. So there's always a group of patients who will not be served by a telemedicine process. And those patients we organize to get seen at a slit lamp at particular clinics. So telehealth is great. It's going to really reduce what we do in terms of the volume of work. It's going to make it more interesting. But as I say, it doesn't replace us. We still need the facility to see patients face to face. It's just that we've now reduced very significantly that number and allows us to deploy our healthcare services more appropriately.
Another question from the Carola Bad. She says it's a very inspiring talk, and she's glad that you could join us. She was asking about as you said, it's computer agnostic. Camera agnostic. Your system.
Right.
Would the system function also with ultra-wide fundus images like Optos and California?
Yeah, Optos. Well, so it certainly functions with the IDON camera. It's really interesting. So, of course, we've got traditional camera systems. We've got Topcon cameras. We've got Canon cameras, Zeiss cameras, which have trained a lot of the data set. We've obviously, with newer camera systems, we've got the IDON, the Triton, for example. So looking at those camera systems work very well. Those systems, when you really blow up the macula, they pixelate that very central macula. I don't know if any of you have noticed that. These IDON pictures look beautiful. Then you make them quite big and suddenly realize that I'm finding it difficult to know whether I'm looking at a microaneurysm or whether I'm just looking at a pixel. Mm-hmm. So these wide field camera systems, particularly these false color camera systems, can be very interesting. So it certainly works on the IDON. We've got a separate validation data set to say it works there. Optos is a different beast. Again, it's a very, very valuable tool. But because it does really peculiar things to the peripheral retina, does all sorts of strange aberrations, that's potentially less usable. That's not to say impossible. And we've got a very large, what I didn't say is running alongside our diabetic eye screening program, we've got something called the photo monitoring program. So, of course, the other issue we have in diabetics is you've got all these patients who have moderate disease. They don't fit the criteria for screening, and they sit in our clinics on annual reviews or 6-month reviews because they've got severe disease, but they don't have proliferative disease. So we put all those patients into a photo monitoring program, which we run by the Optos. So we've got an Optos bank of photographs of many thousands of patients. So we will start to deploy the AI mechanisms on Optos, but I think Optos is going to be challenging because it does pixelate. I'm sure any of you have seen an Optos picture and it looks like a blocked hemorrhage, and then you look at it and it turns out to be a new vessel. It can be very difficult just because of what the Optos does.
And I'm assuming even in terms of processing the images, they're very large, and I don't know how they would be tackled to a system that's familiar with only Topcon images with smaller.
But some of our Topcon images are 1.2K by 1.2K pixels. So these are big images that the AI is processing. Of course, there's a trade-off between the size of the image and the processing time taken. So we've just published something in PLOS where we sort of played about with, do we increase what's the trade-off between the size of the image that you're doing and the time it takes to process, and where's that balance such that you get a good blend of it? But those are certainly questions that we're happy to take later on from the technical team to answer how we sort of played about with that.
I'm sure you would. Dr. Sulaiman is asking about how do you calculate the amount of data you need to train the AI system and to know that it's reliable, and how much time do you need to create an AI system?
Wow. How long did it take? Well, looking at our data, the trouble is, if you look in the early literature, you'll find people who used, 400 images to train their AI. It means it will work on those images, but it won't work on an image which is slightly different. So the bigger the database, the more generalizable it is. Let's take my example of chickens, for example. If you train it on red chickens, then it will pick up red chickens. If you train it on red chickens who are not only standing but flying and doing all sorts of things, it will pick up all those. If you train it on chickens which are black chickens, red chickens, and some of them are flying, some of them are roosting, some of them are sitting, some are walking, then it will pick up every type of chicken, but you need many more images to do it. So the issue about the number of images is all about how generalizable is your AI going to be. So as a rule, several 100,000 images are required, and they have to be representative of the group you're looking at. Again, the difficulty we have with AI is, particularly with healthcare, is that often the number of patients who have the disease is really small compared to the number of patients who don't have the disease. And so you have to address that imbalance within your data set.
Okay. A couple of questions from our optometrist colleagues, and it seems that they're interested in being part of
Mm.
such screening program. Do you think there is a program? I mean, given that most of our optometrists are in practice mostly doing refraction, do you think that there is some sort of refreshing course or any special program that should be provided to them in order for them to start? Or do you think that the basic training that you get from 5 years in college and an internship would be something that makes them ready to work with in a screening system?
Yeah, we've wrestled with this question for a while, and we often find that our graduates coming out of optometry school here in New Zealand are really keen, but they have often not seen much disease. Sitting in the refraction clinics and sitting in the optometry clinics, they'll see a lot of patients with normal fundi, and they will have had lots of lectures about patients with disease. But again, looking at diabetic retinopathy, 3-4% of patients with diabetes will have significant retinopathy. So you'll have to see a lot of patients with diabetes to see disease. So we have taken their core enthusiasm and their ability to learn, and then we have trained them specifically, because it actually takes time to recognize that this is a branch retinal vein occlusion and not moderate non-proliferative disease, or it's a central retinal vein occlusion, or is this macular disease, or is it drusen? So there's a lot of pathologies that we are seeing. Now, one of the spin-offs of our AI is that we have hundreds of thousands of appropriately labeled images. So we've now got big image data sets which are appropriately labeled, and we can put our optometrists or our potential graders through training systems now and say, okay, we can validate you. So,
probably even online now that we're using more of the remote training.
Exactly.
I have a question also from Prof. Marwan Abu Amma. He's asking about the sort of support that was offered by the Ministry of Health during the project. I'm not sure if you have a similar system. We have a Ministry of Health controls part, maybe the largest part of the largest part of the care providers in Saudi Arabia, but it's not the complete provider. Basically, my understanding is that you basically run one system that covers most of the population. Is that correct?
Well, yes and no. So New Zealand is divided, as I said, into 20 different health boards. So the Ministry of Health oversee those different health boards, but the health boards themselves have great autonomy. So one of our, we do have standardized grading criteria that all health boards should adhere to. We do have a basic key performance indicators that the health boards should be reporting to. But above and beyond that, it's left to the health boards to decide how they're going to meet those criteria. So a lot of our work has been about going around the country, talking to people who are involved in screening and getting them on board. So I don't want to give the impression that we have got a completely national system just yet. We're still in that process. If you look at my roadmap, we are in the deployment phase. So we're just beginning to deploy this around the country. The Ministry of Health, to be fair, are very enthusiastic. They do like what we do. They have given us, apart from encouragement, they've given us very little support. A lot of our funding has come from the Ministry of Business, Innovation and Enterprise, to be fair. Okay. Which is why we had to set up a company to get this off the ground, because we had to fund it somehow. But the ministry are very keen, and particularly in the COVID crisis, suddenly telehealth has become the key topic. So they have been somewhat reluctant at the present time to impose a national program on all the DHBs. But in post-COVID time, actually, we're going to need national solutions for our telehealth solutions. You can't have multiple telehealth programs. You need probably one or two, particularly for a small country like New Zealand with only 5 million people. So we are in discussion with the ministry at the moment and hope that actually the crisis will come out of it some good things. And one of those good things will be an acceptance that there are some programs that do have to be run at a national level, delivered locally, but run nationally.
Okay. A question from Dr. Aurora Abad again. She's asking if you noticed any trend in reduction of the number of patients of advanced diabetic retinopathy. after
Yeah,
you?
so that's again really good question. Of course, we've been looking at patients with diabetic retinopathy now since 2008, and I suppose the big thing we find is that there are patients who attend screening, and there's patients who just walk into your eye clinic with a vitreous hemorrhage.
Mm-hmm.
So of course, our really bad patients, the ones who are not engaged with healthcare.
Mm-hmm.
So to answer that question, you really need to know how many patients are walking in as an acute with sudden loss of vision due to a vitreous hemorrhage with a tractional retinal detachment in their other eye. So we certainly know that, having run our screening programs for a long time, that the number of patients walking into the emergency eye clinics up and down the country with sudden loss of vision due to advanced diabetic retinopathy is much, much lower. Our incidence of rubeotic glaucoma due to advanced diabetic retinopathy is, I wouldn't say zero, but it's now near zero. So we're seeing a lot less of these advanced diseases because patients are engaging. However, having said that, we still have this challenge of that hard to reach cohort of patients who just won't engage. They don't believe they've got diabetes. Doesn't matter what you say, it's
There
difficult.
are other tools maybe to reach them other than just having a system ready. I have a question from Dr. Abdurrahman Al-Saadi. He's actually doing his fellowship in more fields now, and he's been working with Peer Skin and
yeah, well,
who are doing some interesting stuff there. And he was asking a couple of questions regarding the ability of the AI system to detect non-DR but referable conditions. And do you think it's essential for the DR screening program to include this? This is another question that was also addressed by Dr. Sosa Nuwailati. And regarding the normal subjects who were screened, which quality measures do you suggest to be sure no patients were missed? I mean,
yeah. So, there are multiple issues raised here. First of all, you need to know what your non-diabetic comorbidities are. So as part of our program, we collect a lot of information about our diabetic patients. So we record if the patient's got hypertensive retinopathy, if they've got macular degeneration, drusen, nevi, epiretinal membranes, glaucoma suspects. So at the time of our screening, we have always collected all this information. So we just in the process of publishing a big audit of the comorbidities that we see at the time of screening. So in our population, the sight-threatening comorbidities that we see are macular degeneration. The older the patient gets, the more likely that is going to be an issue. So of course, our AI is only going to sign off those patients who have no abnormality in the fundus. So the patient's got drusen, it's going to flag that up as an amber because it's going to suggest an OCT. If the patient's got a branch retinal vein occlusion or a macular hemorrhage due to AMD, it's going to pick up the hemorrhage and flag it up as a potential M4, M3. So you're going to pick that up. The glaucoma suspects are an interesting group of patients. It will certainly pick up if the patient's got a advanced hemorrhage at the disc, it's going to pick that up. But if the patient's just got an enlarged disc, potentially an issue. In our cohort, it's about 1% of patients are called glaucoma suspects. And of those 1%, maybe less than a third actually have glaucoma. So we're talking about a very small number of patients. So of course there's Google and the such like, you can read those. There's lots of work being done to pick up non-diabetic pathology. We've taken a slightly different approach. We basically said, if the fundus is completely normal, we're going to sign it off. But if it's not, then we're going to get someone to look at it. Now that still means that the whole process is not automated, but it means we can sign off 75% of our images on first grade, which is still a massive saving to
very good number. Yes, exactly. A question from Dr. Hassan Al-Dibi, and he was asking about the orange zone or the amber zone that you have. Could it be subdivided or graded regarding this?
Well, that's the beauty of building your own AI. You can set those thresholds wherever you are. In fact, we've got multiple different, again, we just published a paper where we've just used multiple different sensitivities and specificities. So you can draw the line wherever you want. And you can say, well, do I want an AI which is going to just miss nobody? So the sensitivity is going to be very high, but the specificity will be quite low. That's okay. I'm still going to sign it off. But having done that, do I then put those images through a second AI, which then says, I don't want to miss disease? For example, we may have patients in the eye clinic who we are thinking, well, maybe we can use our AI to triage all these patients who now need to be seen post-COVID. So we've not done anything for 6 weeks, 4 weeks. So we've got a whole cohort of patients who have not been seen, and we were already busy enough. So can we use our AI to push through all our eye clinic patients and then find out those who've got maculopathy which needs treating? Because of course we've got a huge backlog we've got to get through. So again, you can go back in the AI, change those sensitivities, specificities, and say, I want this to pick up exudate or new vessel. So that's the beauty, because we own the AI, because it's our AI, we can redevelop it. We've had multiple iterations already.
That's very exciting. I think this is very encouraging for us to have our own. A question from Dr. Abdullah Aoun. He's asking, do you consider developing algorithm that can detect peripheral pathologies? That recent papers showed looking in peripheral retina using AI would yield more information compared to the posterior pole in terms of diabetic retinopathy. I think this is something that a lot of people has discussed with.
Yeah, it's all about having the right data set. So anybody who's taken lots of photographs really will realize that it's sometimes not that easy to take a good quality picture of the peripheral retina. And what we call the peripheral retina is actually the mid-periphery. Your VR surgeons will realize that most of the peripheral retina are just not easily visualized. So you have to be careful. What do you mean by the peripheral retina? In actual fact, if you're talking about a fundus camera system, you're talking about the mid-periphery, not the peripheral retina at all. And in our diabetic eye screening program, patients with type 1 diabetes, we don't take 2 pictures per eye, we take 4 pictures per eye to catch the inferior and superior peripheral retina. Okay. So we have, that's already in our system. I didn't explain it because it's just for sake of brevity. We've also undertaken a large audit of all the patients who we've taken 4 photographs as opposed to the 2 photographs. In reality, having those extra 2 photographs almost never change the outcome for the patient.
Oh, okay. Which is very encouraging, I assume.
Yeah. And bearing in mind, if you have to ask patients to take photographs of the mid-periphery, that's quite challenging. And so you need a different grade of people taking the photographs. So if you want someone who can literally just, with a day's worth of training, drive a fundus camera, taking a disc and macular photograph is easy. Taking good quality pictures of the peripheral retina is much more challenging.
Yes. Another question about from Dr. Mohammed Adli about having your own normative data, or you can still use the open source data that's available. And this also links to another question, talking about demographics of persons like age, gender, ethnicity. Was it linked to certain biomarkers in your data set that you
Yeah. Of course, there are lots of open source data sets out there. We did a lot of work originally with a Kaggle data set. It's a great data set, and what an amazing resource to have available. But again, on the whole, it's a largely European data set, and so it can take you so far. So you can play with a Kaggle data set, and it allows you to really get to grips with the basics of AI. But ultimately, you have to then start using it in your own population. Now, the other part of the project, which I've not spent any time talking about today, is that obviously we have all the data for those 60,000 patients over the last 10 years. So we've done very big statistical modeling to say, okay, what are our, looking at logistic regressions and likelihood ratios, what are the key factors within patients with type 1 and type 2 diabetes which predict progression? Because of course, the other piece of the puzzle here is, okay, I've screened the patient, what happens next? When do I need to see them? So we have also used our statistical data set to create a calculator based on a couple of key indicators that the data itself revealed, like ethnicity, HbA1c, duration of diabetes, etc., to know when I should screen that patient. Ultimately, the AI will probably do all that as well. You take 1 or 2 photographs and it will say, the next photograph will look like this, and therefore this patient who's got mild disease doesn't need to be screened again for another 3 or 4 years. Or this patient, even though it doesn't look too bad, they're a certain ethnicity with bad sugars, who've had diabetes for a long time, they're going to be a rapid progressor. So it really does allow us to deliver personalized medicine to our patients in remote areas on the fly. You know, the power of this tool is quite phenomenal.
And this term personalized medicine takes me to some people, some question that's been repeated by a lot of our attendees. Everyone is asking about having a certain kind of camera that will be portable and that can help in taking images of the fundus. I assume this is the holy grail, let's say, of
Exactly.
where
So
you
yeah, the holy grail, you know, the holy grail, I suppose, is to get your iPhone or whatever it is, have an attachment and take a photograph. So, you know, over the years, there have been various groups who have produced an attachment. And of course, when they go on stage and show you how to do it, they can do it, but then you go and try and replicate that. It's very difficult. So the issue we have at the moment is actually having some form of optics which will allow your fundus camera to take your photograph. You know, that's the ultimate thing, is that all you do is you get a text, say, it's time to take your photograph. You give your phone to your wife or to your brother and say, please take my photograph. You upload that to the cloud and it's done. So of course, that is the holy grail. So we have spent a lot of time looking at a number of different portable cameras. Again, it's really quite challenging. I don't know if any of you have tried it, but it's really quite challenging to take consistently good photographs with some of these mobile cameras that are out there, which then really limits the utility. I'm sure these camera systems will get there, but at the moment, there's a couple of technical issues which make them difficult to use.
I have the final question, because I've kept you more than we planned, and I'm very excited that you've given us this valuable times of yours. This is a question from Dr. Rayyan Sharif, and he's asking. The question is: so you can have you linked or considered linking the OCT images to the fundus photos, so you can know which of these evaluated patient needs semi-urgent care examination by its subspecialty? OCT variations are considered easy to detect, and with the increasing number of diabetic and future diabetic DR patients, this could be valuable. Any thoughts about that?
Yeah, so you know, we're very blessed. Not only do we have OCT, we actually have OCTA on our central system. So that's a whole new ball game, isn't it? Can you actually can you determine the level of peripheral retinopathy just by looking at the microaneurysm count within the central macula? But I digress. So the purpose of our system is that the OCT is also sent down the telehealth system as well as the color photograph. So obviously in time, the idea would be an AI which is reading those OCTs as well. Mm-hmm. But OCT takes time to do, and you don't want to be OCTing everybody. Of course you can do in an ideal world, but that has a resource limitation and implications. So we have, you know, we reserve OCT for those patients who we believe it's going to make a difference in terms of the outcome. So that's all patients who are red with a macula and all people who are amber with a macula. Mm-hmm. And so when that image is then graded by the ophthalmologist or whoever's reading those images, they will have the OCT to hand as well. So yes, the OCT is critical to make sure that the right outcome is given to the appropriate patient.
And that's the ultimate goal of what we're doing here. Thank you very much for your time. I appreciate the time you've given us and this valuable insight. I'm sure this is something that anyone that wants to go into this field and getting to help this huge amount of patients with this technology will be using this roadmap as a very important tool in this process. So I would like to make a couple of announcements. One of them is actually that we, alhamdulillah, we've managed with the help of the hospital in King Khalid Eye Specialist Hospital and the help of others in THEIA Valley to create our own artificial intelligence model, where we actually are deploying and in the state of validating it against our patient population at this stage. and hopefully we will get to learn a lot more from you guys and what you've been doing. The other announcement is that we do have an exciting lecture, 2 lectures actually next week, and like this one, we are also pleased to have another lecture about this hot topic, artificial intelligence, and this will be given by Piers Keen, who's a member of the DeepMind team and that works with the project of Google, and he's going to talk more about the future of artificial intelligence in ophthalmology. This is on the 22nd of April, so save the date, and we'll post the links also. And the 23rd at 6 p.m. we will have Dr. Tamer Mahmoud. Dr. Tamer Mahmoud is a very well-known VR surgeon who's part of the Royal Oaks team in Michigan, and he will be talking about macular holes and social isolation. Can flaps and transplants survive COVID-19? I think it's going to be a very interesting talk for our VR surgeons as well. Again, I want to thank you again, Dr. David, for this time. I see that Dr. Abdelaziz Al-Rajhi, is our CEO, is interested to also add something, so I'll leave the mic for him as well.
Thank you.
Hello, Dr. David. This is Aziz Al-Rajhi, the CEO of ClickEdge. I wanted to thank you so much for your time. I know we took way too much than what we've asked you for, but it has been a very interesting topic and a very beautiful presentation. And as you see, because it's been so interesting, people won't let you go. We all didn't want to let you go. We appreciate what time you've given us, and we are very happy to hear about your experience, and we hope that this will open the door for the future collaboration between us and you, hopefully as soon as we get off all of this crisis that we're all going through. So thank you again, and we wish you all the best.
Thank you. Well, finally, thank you very much for inviting me. I've really enjoyed getting to know you, your team, and yes, I'm really keen to see where this takes us. So once again, thank you, and thank you for listening.
Thank
you
very
much. Have a great day. Bye-bye.
Goodbye, everyone. Bye-bye.
Bye-bye.